So we're going to continue our conversation about waves. Two new questions. Our questions are, give me a second. How are waves related to simple harmonic motion, and what exactly is a wave? So the last video we learned about simple harmonic motion, so we want to say how does that link to this, and then what exactly is a wave in and of itself. You got 6 terms for today for this video. You've got medium, mechanical wave, electromagnetic wave, transverse wave, longitudinal, and pulse. So those 6 terms. There's a small chance we won't get to pulse, just in case it'll show up again. All right, so first, how does simple harmonic motion relate to a wave? Okay, so I want you to picture that spring bouncing up and down. Here, this video right here, you're going to see, we're going to watch that spring bounce up and down. So we're looking just in the middle, okay? So we're just watching it go up and down, okay? But if we were to take this up and down and we were to stretch it out over time, you see how this works coming along here. All right. You also see over here how it links to circular motion, the up, the complete down. All right. You're getting the same thing happening with a wave. So that is how simple harmonic motion is related to waves. If you were to take a simple harmonic motion and you stretch it out over time, you get a sinusoidal wave. Okay. And now, how's that going to work for a period of a pendulum? All right, I'm going to get kind of messy here. I'm going to get this image out of the way just for a second. Okay, so here's what I want you to think about. I want you to think about, okay, the pendulum swings back and forth, back and forth, back and forth, back and forth. Now, again, if I start stretching this out over time, all right, you see how if you're a little bit neater than I am, all right, maybe we could try this a little bit small. Oh, maybe we could try it smaller. Okay, just one second. Let me try this one again really quickly, just so we can see if we can be a little bit neater. All right, we're going to go back and forth. This is what the pendulum doing. It's back and forth, and then I start stretching it out over time. It's a little bit better. You can see that's how the wave happens. So that's how simple harmonic motion and waves are linked. If you were to take the motion, stretch it out over time, you get a wave. All right, so but what exactly are waves? We're taking a look at this pendulum, and what I want to think the last time we talked about pendulums. The last time we talked about pendulums, I believe, was with energy. That's where at least it came up. So I'm going to move this back. Can't see my lovely face. All right, we're going to come up here. We're going to look at this again. So, but we're going to look at this not with waves, but with the idea of energy. Okay. So when you pull this up, and it comes up to here. Whoops, not there. Here. It comes up to here. That is the maximum height. Okay. And at this position, it has a maximum potential energy, and it has a kinetic energy of 0 joules. As it falls, it's going to get faster and faster and faster until all the way it comes down here. This right here, this place, is its minimum potential energy, okay, or rather potential energy equals 0. And we have a kinetic max. And it's going to come up here. And then there again, we have a maximum potential energy, and kinetic energy is equal to 0. And it's going to keep doing this back and forth over and over again until finally the restoring force has worked its magic and it's at equilibrium. Remember, equilibrium is that blue line. Okay. So we looked at that. So that's what a pendulum is. That's how we've known about it. Same similar thing that happens with the spring. We can move this down just a bit. Okay. When you pull it down, this is maximum spring potential, and you're holding it, so that means your kinetic energy is equal to 0. As it goes back up, it's going to speed up until you get to the equilibrium position where the velocity is 0, kinetic energy. I'm sorry, that was totally wrong, wasn't it? All right, we just had kinetic energy is equal to 0. All right, where this is its maximum velocity, excuse me. So it's the maximum velocity maximum kinetic energy, and that also means our potential energy is equal to 0. It's going to keep coming up and it's going to compress a bit, and then it's going to hit some space up here, and that'll be the other maximum potential energy. That maximum potential energy, that's where it turns around. Think about when you throw a ball into the air, when you turn, something turns around, its velocity is 0 and its kinetic energy is 0. So what we just did there was we looked at both the pendulum and the spring in terms of energy. Okay? All right. So all this is to show us that simple harmonic motion is about... So simple harmonic motion, let's get that pen back. So simple harmonic motion, we know relates to waves. That's what we saw. You stretch it a simple harmonic motion out over time, you get a wave. And simple harmonic motion also relates to energy. All right, so that is where we can say that waves, therefore, must also relate to energy. More specifically, we're talking about a mechanical wave. Okay, where a mechanical wave is basically, it's a disturbance that moves energy through a medium. Okay, I want you to get this. A wave is just energy moving through a medium. That's all it is. It is just energy. It does not matter. It is energy. Waves are energy. Waves are energy. Now the question is, what's a medium? All right, medium is just what the wave moves through. Right now, my voice is as a sound wave, okay? And you can hear it. It's going about 343 meters per second. But if I were to try and talk to you underwater, that's a different medium, so that it's going to sound really different, and you can't understand what I'm saying because it's going to be at a different speed and different wavelengths. Okay, now this entire concept of medium, and that a mechanical wave has to travel through a medium, is also why certain movies that shall remain nameless are complete bunk. Because if you think about certain space movies, and they have these huge explosions happening in space, and we can hear them. Okay, but you're smarter than that. You know that we can only hear things that travel through a medium, and space is just a vacuum. A vacuum means it's nothing at all. There's nothing in this space. So if there's nothing for a sound wave to travel through, you can't hear sound. So when we see a movie and it shows a big explosions and pew, pew, pew in space, they're just doing it for you. They're not doing it for, that is basically anti-physics. Okay. Now let's talk about what can move through a vacuum. So we just talked about a mechanical wave. The other type of wave is, the one I have right down here. It is called an electromagnetic wave. Okay. Now, electromagnetic wave is actually kind of a combination of electrical vibrations and magnetic vibrations. So electromagnetic waves are things that are on the electromagnetic spectrum, such as light, radio waves, microwaves, gamma rays, anything that is like that is considered an electromagnetic wave, and it doesn't have to travel through a medium. So electromagnetic wave, it moves energy, but does not need a medium. So that was your example of electromagnetic waves. Examples of mechanical waves are sound, earthquakes. Let me see, you got anything else we can put in here? Now, sound, earthquakes, stuff like that are kind of working with it. Guitar strings, when you, because it's going through a wire, anything like that. So there's our mechanical wave and there's our electromagnetic waves. But regardless, to answer the question, what is a wave is energy moving. All right, so now the next question, last question is, what is the shape of a wave? Okay. Now there are two possible shapes to the wave, and you're seeing them right here. We've got a longitudinal wave. Whoa, that was not what I wanted. and a transverse wave. Now they're showing this with a bit of a slinky. So we'll do the transverse wave first. A transverse wave looks like what you think it's going to look like. It's got this entire up-down ocean wave thing going on. Basically, what happens is we say that this will work. We say that the matter, right here, this part right here, the mass moves up and down, but the energy is moving sideways. So we say that the matter is perpendicular to the movement of the energy. Now the longitudinal wave over there, right? Now remember, longitudinal wave is a bit different. In this case, we have, it looks funky. Think of a picture of a tuning fork that's vibrating. Okay, so as the tuning fork vibrates, all right, it pushes on the air, it pushes that air out, and as it does so, it causes these compressions. It gets really close in there, and then it spreads out again, and then, all right, so we have those little areas of compression, and then it stretches out, and then there's a compression again, and it keeps going kind of like this. So with the longitudinal wave, what we say is that the matter is moving parallel to the energy. Okay? All right. So before we finish this, I just want to show you a couple of simulations for the longitudinal and transverse waves. So first off, this right here is a picture of a transverse wave. You can see it's going up and down. I want you to watch, look right here. This is the mass. See where my cursor is? All right, I want you to see something. That mass, that matter is going up and down. Okay, all right, that's moving up and down. But you can see that the energy itself is going sideways, going left to right. So that's our transverse wave. It's a little bit easier to see. Here's where to go. Why are we not scrolling? We're almost done. Okay, here is a transverse wave. Notice you can see in here, if I find my cursor. All right, see right here, this red dot? That is a single piece of matter. That matter just goes back and forth, like if you push a slinky out. Okay, so it pushes, all right, and when it comes back, it looks like pushes, 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 pushes. Okay, it pushes on all these things right here. Those are called, well, we'll get to what those are called in our next lesson. So at this point, Susan, what are some examples of longitudinal waves? Okay, longitudinal waves are, excuse me, my brain stopped. I suddenly got a fear that I said something wrong. Give me 1 second. I'm going to check back here. Nah, we're good. Okay, so mechanical waves are the type of mechanical waves. We can break them into transverse and longitudinal. Now, transverse wave is going to be ocean waves. That's your guitar string one. The longitudinal wave is most commonly known to as sound. So our examples here. Is sound. Example here is ocean. Okay, so that basically covers, that should be covering our original questions. Let me see, I think, we talked about the word pulse. That's one last thing to talk about. And here's the last little bit. What you're looking at is a series of waves. It's continuous, it's oscillating, it's going back and forth. So the difference between that and what a pulse is, I'm just going to reset this button here. All right, is a pulse, rather than a continuous oscillation, a pulse is just a single bump, a single wiggle. Take the damping down here. We're going to talk more about this. So if you see the word, if you hear the word, you know what it is. That is what a pulse is. Okay, it is a single one. Here's another pulse. All right, and they're kind of interfering, and they're doing all sorts of funky stuff, and we're going to learn about that funky stuff later. But for now, I want you to go back to those original questions. the top of the page. How are waves related to simple harmonic motion? What is a wave? I want you to go to those terms and make sure that you can answer those questions and that you know what those terms are. And we'll see you later.